And then we get to screen sharing. Uh-oh, what just happened? Search. There we go. Okay. So we were here before. I'm not really sure why the projector decided to turn off by itself. So that's kind of interesting. All right. So what we're going to do today is to talk about your next homework assignment. This is not one of those where you can finish it during the lab time. Okay. So I am going to the lab after today's lecture. You are encouraged to go to the lab and get started with this activity, but it is not something that you can finish during the lab time, which basically means the due date is going to be not today. Okay, so it's going to be March 7th, which is next Tuesday, right before class. That's the due date of this particular activity. But what I do need to do today in class is to explain what it is, how to use the tool, how to set it up, and what you're supposed to do. Okay, so that's going to be the first part of today's lecture. Depending on how much time we have left after that portion, then we'll also look into a new topic. We'll start to look into a circuit in LogicSim to implement the most basic quote unquote memory feature inside a computer. So we'll kind of split the class that way today. So without any delay, we are going to go here and then we'll take a look. All right. And I'll do a preview. So we'll take a really kind of close look, step by step into what this lab or homework assignment is about. So this is going to be great for people who have been itching to write programs, because I know many of you think of this as a programming class, and up to this point, we design the circuits, but we really have not written any code yet. So this is a programming assignment. The programming language is going to be C or C++ if you want to use object-oriented programming, which is not necessary. So we'll go ahead and look at the description of the assignment, step by step, and then I'll also introduce the tool that you need to use, in the process. All right, so I'll just go ahead and read this from the beginning. This assignment involves completing the E10 to E2 function in C code. You can use online GDB to write and test your C program as a single file. So because this is a hyperlink, so that means you might want to download it. So by right-clicking and then clicking on Save Link As, this way you can download it. And the name of the file you're going to download is monolith.c. So do not be alarmed when it asks you to store a file called monolith.c. Okay, it's just a plain C file. It's not even C++. So I will save it to my temp folder, which is going to replace the file that I have there already, but that's okay. So The rest of this assignment is requiring you to write some code in C and test it. So the question is, are we going to do that? Well, the answer to that question depends on how comfortable you are with the various tools. So if you have code blocks already installed and you're very comfortable with code blocks, use code blocks. If you already have, what is it from Microsoft? Visual Studio, VS Code you already installed and you feel really comfortable with VS Code, use VS Code. If you're like me, you're comfortable with the command line version of GCC and GDB and Vim and stuff like that, use those as tools, okay? If you are none of the above, okay, and you say, I refuse to install anything on my computer, or all I have is a Chromebook, okay, I cannot install anything. Actually, that is not true. You can actually install Linux on a Chromebook, okay, and it's pretty easy to do it. But if you don't want to install anything, we can use online GDB, okay? So that's another way to do this homework assignment. Yes?
Is it possible to use Replit, or does online GDB have something that?
I am not very familiar with the debugging capability of Replit. I know what it is. I try to use it from time to time, but I'm not really sure about the full capability of Replit in terms of debugging. Yes?
I believe Replit has supposed to do better. So weird about that.
Does or does not?
Yeah.
I cannot remember what you said.
I don't think it does.
It does, but it's limited.
It's limited, yeah. That's what I remember too. So online GDB is not a bad tool for this purpose. I have used online GDB for a lot of stuff already, and I find it to be quite useful. Okay, so that's one option. So I'll go ahead for the rest of this instruction. I'm just going to assume that you're going to use online GDB. Okay, but you are more than welcome to use any other tool. So I'm going to head over to online GDB, and I want to make sure that I did not sign into anything because I want to show you what it looks like if you do not sign in. And I'm pretty sure I'm not signed in because it has signed in, log in as a prompt here. Okay, so the only thing that you have to be careful about when you use this tool is if you don't sign in and you don't save the file, you can risk losing your code just by closing that tab in the browser. So keep that in mind, okay? So one thing you can do is just log in using a particular Gmail account. So I'm going to go ahead and do that. Go to login. And it does allow you to use Google Plus, which is your Google ID, Facebook, which I do not have an account anymore, or GitHub, to sign in, or you can just basically set up an account, separately and just use something entirely different. So I'm going to use Google Plus and use one of my two accounts here. I'm going to use my personal account. Okay, I don't think there are any actual code here. Okay, so once you sign in, this is great because now you can use online GDB and it will actually save your files. Okay, so you can now go to, okay, so let me show you how to copy and paste the code first. So I'm using a command line interface. Yep.
Is this being recorded?
Yes, because Zoom has this kind of little glowing red button thing. So I think we are being recorded. And the online people have not complained yet that they are not hearing anything. So I think we're good. It is entirely possible that all the people who are on Zoom, they're all cooking and doing garden work and whatnot, and not actually be there. That's entirely possible. I cannot tell. All right. So in my case, okay, to get the content into here, it's a little bit cumbersome. So I'm going to use this command. It's not going to work for the rest of you because it is a Linux kind of thing. But this allows me to copy the content of a text file into the clipboard, and then I can switch over to the browser and then do a Control-A, select all, delete, and then Control-V to paste the actual content of that file. So after this, the next thing you need to do is to select a programming language. So as I said a little bit earlier, the program itself is just a plain C program. So if you were to select C, it would work. But if you want to use C in and C out for debugging purposes, which I do not recommend, but it's up to you to choose how you want to debug your program. So if you say, I only know how to use C in and C out to debug a program, then you will need to select C++, because otherwise it won't know how to use C in and C out. But I just want to use C, okay? Because I do not recommend the use of C in, C out for debugging when you have a debugger. So after this is all done, the next thing you want to do is to click on this button here. And nope, sorry, not that one. We want to save the file. Control S would actually trigger, oh, okay, it saves from the browser's perspective. And I'm not quite sure. This is just going to create a new file. Save. Okay. So click on save, and then you have to create a new project name. So I'll just say negative exponent. You can make a destination. You can create subfolders if you want to. So I'm just going to save it under my projects. Click save. So now every time I save the file, it is saved in the cloud, and I don't have to. There's no risk of losing the content of my edits anymore. Is that part okay? Does everybody kind of understand how to set it up? Okay. So you do want to be able to sign in. It doesn't cost you anything. So if you don't want to risk having your account being spammed, you can always just sign up for a brand new Gmail account just for this purpose. Right? I can just sign up in a new account called tag CISP310. It's only for this purpose. Okay. All right. So are there any questions? No questions? Okay. So don't forget to save the file. Okay, periodically save your file. So I'm going to switch back to the description. So your code should take a struct float 102, 10 to 2, pointed to by parameter Pn, and preserve the value of V, which is the coefficient C, times 2 to the power of E2 times 10 to the power of E10, and the restrictions are as follows. The resulting coefficient C, which is member coif, should make the condition blah, blah, blah true. And then we have E10, which is member E10, should be 0 when your algorithm is done. And then member E2 can be any integer. The represented value V, which is calculated this way, should be preserved as much as possible. And then your entire program should not use anything that relies on float, double, or functions from the math.h header file, and then to comment your code. Okay, so I'm just going to pause here and see if you guys have any questions. So if your question is, what do you mean by E10 and E2 and the coefficient? That's the stuff that we talked about on Tuesday. Okay, so you might want to rewatch the lecture on Tuesday. Yep.
So we're just trying to display our own kind of flow, basically.
Not to display, but to convert. Yeah, it's a conversion process, which is what we talked about on Tuesday. So we are actually writing the C code to do the conversion now. Yep. So that's why this homework assignment directly relates to the lecture on Tuesday. So if you want to, the Tuesday lecture is already online, it's on YouTube already. So you can basically rewatch that in order to get a better understanding of how to do this. Okay. Yep.
Has coef or whatever in the
Correct.
code.
Yeah, coefficient.
Yeah, that's just C that we talked about last time.
Yes, it is. It's basically serving the role of the
Specifically
symbol C.
not C2, right? Just C.
It is C. I cannot use the term C2 because the coefficient is not specific to just base 2.
Sorry, I read this C2.
Okay, so it helps if I just kind of test run the program and show you guys what function you're supposed to complete and what is given to you already, which part you do not have to do, and which part you do have to do, okay? So we'll go ahead and switch back to online GDB. And the main function is already done. So don't touch the main function. You don't have to do a single thing to the main function. You just have to go to the function that I was talking about, which is E2 to E10, or the other way around, E10 to E2. Sorry, there we go. And it is right here. This is the prototype, but I cannot remember where I stashed the actual body of the function. Way at the bottom. Okay, so let's right there. Yep. Okay, so it's on line 121. This is the entry point of the subroutine, and it is empty because it is your job to fill in the content. So it looks like we got a person who's signing in just now. There we go. Okay. All right, so so this is the function that you have to implement something, and then the first question is, what is given to this function? Okay, you know, how do I run this code? How do I actually get started with this? Well, that's also in the instructions of the assignment. So we'll go ahead and continue reading the rest of the instruction. So in GDB, in the GDB console of online GDB, do the following. Put a breakpoint at the end of E10 to E2 when you're done. You can click slightly to the left of the line number to toggle a breakpoint. You can also toggle a breakpoint by clicking, oh, okay, I just repeated myself here. After compiling, use this command to run the program with a test case, and the test case in this one is 1.23 E, which is times 10 to the power of -10. When the program stops at the breakpoint, you can examine the expression. Okay, this is typo. It's supposed to be expression asterisk pn using the GDB command print asterisk pn. Okay, so we'll go ahead and perform all of these steps. Okay, because when I do it once, you guys can visually see how it is done, and then you will have a much better idea of what you're supposed to do. So I'm going to switch over here, and as I said a little bit earlier, kind of go to the left-hand side of the line number. Click in order to set up a breakpoint. Is that part okay? Okay, super easy. And then you want to start to run the program. So when you're going to run the program, you have to go to debug, not run. So that's what I'll do here. I go to debug, click on it. It's basically going to compile the program. So when it's time to run the program, I will have to follow my own instruction. So my own instruction is to say, do a R, which is run, -n, which is a switch on the command line, and then whatever base 10 scientific notation that I want to convert. So in this case, it's 1.23 times 10 to the power of -10. So I'll go ahead and just do that. Okay, so we go to online GDB, do a R, -n, do not forget the -n, okay? It is necessary. And then we have 1.23 E -10. So by the time I press the enter key, it will start the program. And if you put your code into E10 to E2, it would run your code. Are we good so far with this process? Okay. So I'm going to press the enter key right now. And since I did not have any code whatsoever in E10 to E2, it gets to the end of the subroutine right away. So how do I know it is at the end of the subroutine? You can see how this line 126 is highlighted by the bigger green rectangle. That's the indication that I have paused the execution of the program on line 126. Is that okay? So the other clue that I'm currently at a breakpoint is right here. It says breakpoint 1, E10 to E2, blah, 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 on line 126. And then you can also see the GDB prompt is back, which means I am now ready to do certain stuff. So what I said earlier is to say, is to print asterisk pn. Asterisk in this case is the dereference operator, and pn itself is a pointer, okay? Because you can see pn is a pointer to a struct float 102. And 102 is from base 10 to base 2. That's why I named it as 102. So are there any questions right now about the prototype of the function? So you are all comfortable with the parameter being a pointer to a structure? All right, okay. So when I press the enter key in GDB, it will give me several values. I know it's harder for people in the back to actually see this, but all it does is to say, S, which is a member of the structure, equals to 0, because the number is non-negative. Okay, so S is the sign. Remember the sign bit? Okay, that's basically what S is as a member. Coif, which is coefficient, it is corresponding to symbol C in the discussion on Tuesday. And it is 123, okay, because the objective is not to rely on double or float. So we need to convert everything into integers, signed or unsigned. So in this case, the coefficient is 123. But if the coefficient is 123 instead of 1.23, then the power of 10 or the exponent of 10 cannot be negative 10 anymore. Now it has to be negative 12 because I need to maintain the value being represented as the product of the coefficient 2 to the power of e2, which is currently 0, times 10 to the power of e10, which is negative 12 at this point. So we good so far? All right, yep.
Did you say that nothing should be with less than 2 to the power of 64?
That's the restriction. When your code is done, that condition has to be true.
So not 2 to the power of e2 times c is less than 2 to the 64?
Okay, so let's take a look. Okay, so let's take a look at the restriction. So the restriction here is 2c has to be greater than or equal to 2 to the power of 64 minus 1, which basically means, if you double c again, it is going to be out of the range of an unsigned 64-bit integer. So it has to be barely fitting within a 64-bit unsigned integer. Does that make sense? Okay, all right. And that's it. That's our homework assignment over the weekend until next Tuesday. Yep.
Can you quickly go over, I think when I was debugging the program, you just put that command R, R dash N 1.2
right.
But how do I restart the program to do a new debugging session? Like if I'm on a program?
Okay, so if you want to restart the program, there are a few ways to do it. You can always just do this again, then it will actually restart the program. So if you're in the middle of a debug session and you say run again, GDB would actually ask you, because GDB is really being kind and go like, hey, you got a program running already. If it's just paused at a breakpoint, are you really sure you want to run the program from the beginning again? You can always answer no at this point and continue the execution of the program, that you have been doing. But if your real intention is to start all over again from the beginning, then you can go ahead and answer yes, press the enter key, and it will start from the beginning again. Is that okay? Does that answer your question?
I think so. Let me try to do that.
Yeah, through the GUI, you can also do it by doing the stop first, and then click on debug again. So you can also do it that way. Yeah, so you can do it the other way as well, and it keeps the breakpoint. So the nice thing is, the breakpoint is actually maintained. So this time I only have to do the run -n 1.23 e -10, and then press the enter key, and then I get to the same breakpoint, and basically that's where we were before. So are we good so far? So I'm going to expect some people will run into the problem of an infinite loop. So the question is, if I do run into an infinite loop, question number 1, what does it look like? Number 2, how do I know where I am in the infinite loop? Okay, which infinite loop are we talking about? And how do I proceed? Once I get into an infinite loop, okay? So I'm going to illustrate that by putting some really bad code here so that we can actually see it, okay? So I am going to go back to stop because once the program is running, we cannot edit the program. So I'm going to stop the program first. And that will give me the ability to go back here and change the program. So I'm going to say while 1, in other words, while true, we say your Pn points to coefficient is going to add 1 to it, okay? This has absolutely nothing to do with your actual solution, so do not copy this. It serves absolutely no purpose copying this, because I'm only doing this to illustrate how to detect that you are in an infinite loop and what to do if you are actually in an infinite loop. Is that okay? All right. Okay. So now that I have done this change, remember, save your file, often, just to make sure that you don't lose, the changes that you have done so far. And because I have signed in already, you can see instead of a log in, I have a log out button. So that means I signed in already. Just the fact that I could save the file indicates that I am already signed in. So don't forget to do that, okay? Because you don't want to lose, the file that you have been working on. So I'm going to take out the breakpoint, okay? Take out this breakpoint here as if, I have never set any breakpoint here. And then go to debug. And then I use R once again, dash N 1.23 E -10. Press the enter key. And this time, you will see that GBD, the prompt, never comes back. So that's a pretty good indication that your program is an infinite loop. Because if the program does work correctly, it would have been done in a fraction of a second. Okay, so what do? Control C, okay? Control C breaks the execution of the program. So type Control C, okay? And then the program will break. Now, you can still continue the execution of the program. It's just that it is telling you that line 128 is a part of the infinite loop. But now that the program has paused its execution, now you can use all the fancy stuff, okay, to figure out why your program is not getting out of the loop, okay? For instance, at this point of time, you can say, I wonder what Pn is pointing to. What is the structure that I'm pointing at right now? So now you can see, I can see E10 has not changed. I can see the sign bit is still 0, but coefficient is some value like this, blah, 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 and so on. Is that okay? So this is how you can, 1, detect that you're in an infinite loop, 2, break out, from an infinite loop, and 3, be able to examine stuff, okay, when when you pause the infinite loop. So one way to figure out why you're in the infinite loop is to single step the execution of your program. So single stepping simply means you're only executing one statement at a time, and you basically want to execute back to the condition evaluation, and then figure out why that condition continues to be true when it really should become false sometimes. Does that make sense? Okay, so I can go ahead and show you how to do that. If you're one of those people who completely refuse to use anything on the command line, you can always use your step over versus step into and just click it. So the difference between step over and step into is if you're calling a subroutine, step over will basically call the subroutine and it will stop or pause execution again after the subroutine has returned. Step into, on the other hand, will actually just perform one single step, which is calling the subroutine. Then it's going to start inside the subroutine that you call. In this case, obviously, it makes no difference whatsoever because I'm not calling any subroutine. I do not believe that you need to use the subroutines either in this case, so it would make no difference whatsoever whether you're stepping over versus stepping into. Are we good so far? Okay. So the other thing you can do for those of you who like doing everything on the keyboard, single stepping is S, okay, which is step. That is equivalent to stepping into. You can also use N, which is next. That is equivalent to stepping over. But as I said a little bit earlier, in this case, it makes no difference. So you can say next. And it doesn't break out. So let me see if I can use a step here. Same thing. So in either case, it does not actually it actually continues the execution of the program in either case. And you can see how the counter used to be ending with 838, and now it's ending with 267. Basically, we have gone through many iterations already. But if you have multiple lines, it would actually go line by line. In this case, the condition is also very kind of stupid because it's a constant of 1. And as a result, the debugger does not even bother to go back to evaluate the condition. So let me check one thing, because we'll go ahead and change the condition to be something slightly more useful and still irrelevant to your homework assignment, because I don't want to give away any code. It is your job. If I do your job, how are you going to get your own job after you graduate? So let's go ahead and make this okay, that's totally irrelevant whatsoever. But it is something that the program has to evaluate. And this is going to be true all the time because we are not doing a single thing with E2. So this kind of goes back to debugging. If the program is not exiting, if you have an infinite loop, the first question you need to ask is which part inside the loop is changing the condition that the loop is depending on to get out. Okay, because if your code inside the loop has absolutely nothing that would touch anything in the condition of the while loop, then the loop either will not enter at all, but if it does enter, it's going to be an infinite loop. There's no reason why it should get out of the loop. Okay, so this is one of those cases. All right, so we're gonna do the debugging again, like so. Run -n 1.23 e -10, and it's an infinite loop. Press Control-C to pause the execution, like so. And then this time you can see how it stopped on line 126, because there's something meaningful here that you can evaluate. So if the loop is infinite, that means Pn points to E2 does not equal to 12 is always true. So you might be curious of what is the member E2 of the structure that Pn is pointing to. So you can now just say, hey, what is it? Okay, why is it not? Is it really not 12? If it is not 12, what is it? And it is E2, not E1. It is 0, because it started off as 0, and there's nothing in this code here changing E2 whatsoever. So now, if you single step, it will go to line 128, and then if you single step again, it goes back to line 126. Single step again, it goes to line 128, and so on. So if you are in an infinite loop situation, you should single step throughout the code until it gets back to the condition to give you an idea of, okay, what is it doing and what am I really checking? Does that make sense? All right. And that's about it. I mean, that's about, and then print has a lot of different formats. So if you want to learn how to use the command line stuff, with GDB, you can always just scream help. And I don't know why it's not returning something. It's supposed to tell me what it can help with. Well, there's always the help button too. So the help button brings you to a blog that gives you a brief guide of how to use online GDB debugger. So, I would just kind of quickly go through this and learn the basics of how to use GDB or how to use online GDB to debug a program. And if you want to learn something even more with online or GDB itself, you can always just look for tutorial GDB, and there are tons of them. Are we doing okay so far? How many people have some exposure to using GDB specifically? Okay, so the rest of the class probably have little exposure because your CISP310 professor did not introduce you to using a debugger. Is that correct? Yep. Yeah, that's something I would like to change, but since I don't teach CISP360, it's really hard for me to change that. Because I think knowing how to use a debugger is much more important than Hello World. Are we doing okay? All right. So are there any questions about the tool itself or what the assignment is asking you to do? Yep.
So I know in the instructions it said it should not use anything like functions from math.me.
Yep.
Or anything like that.
So no log, no power, no square root, no square.
Do you have any recommendations how to go about that? Like, are you like giving power loops with like?
The stuff that we talked about on Tuesday.
Okay.
Because on Tuesday, we talked about the actual logic of how to make E10 go away by using division by 10. But at the same time, we also want to make the coefficient as large as possible right before the division by 10. So we talked about a way to keep doubling the coefficient until we cannot double anymore. And then we do a division by 10, but then we don't want to just do an integer division because that has a constant negative bias. So we want to use rounding, which is adding 1/2 of the divisor first to the numerator before we perform the division. So all of that stuff that we talked about on Tuesday, which coincidentally is also in the reading module, is going to be useful for this. Hmm?
All in that, P10, all that.
So while we're talking about stuff that was talked about on Tuesday, slightly off topic, but if it's not too out of scope, why is the C plus incrementing C by C? Why is that faster to compile than multiplying C by C? Because you had talked about that on Tuesday.
Oh, okay. Okay, so I can illustrate what you're talking about using the sample program, and I just lost connection to the server because it's okay, it saved the file already, so it's fine. Okay, so you're basically looking at something like this. Okay, y is so you're asking why this is preferred compared to this.
Yes.
So, okay, so I can tell you why. It really depends on the compiler. Okay, some compilers can do optimization, others cannot. Line 128 is going to be an addition because you specify an addition. So the compiler cannot say, I'm going to use something else to implement the addition because you specify the addition operator. Line 129, you specify a multiplication operator. Now you are multiplying by a constant, but nonetheless, this is still a multiplier operator. So if you're dealing with an architecture where it has no hardware multiplier, then the first implementation is going to be easy because it's still just an addition. But the second implementation on line 129 is going to cause a dumber compiler to actually say, oh, okay, since you specified a multiplication, I'm going to call a subroutine to perform binary multiplication, which is guaranteed to be really slow compared to a single addition. Yeah, because on an architecture that has no hardware multiplier inside the processor, then multiplication, even integer multiplication, is going to be done by a subroutine. And that subroutine is generalized. So it's not only for multiplication by 2, it's for multiplication by anything. So it's going to go through the whole thing of the shifting and then all the adding. So even though it's not like super slow, it's going to be way slower compared to just adding an integer to itself.
Is it possible that we could run through another example of a conversion from like an E10 to an E2, like from scratch? Okay.
Yes, indeed, I have done it already. I provided something like this, okay? So if you are to use 1.23 times 10 to the power of -45 as an example, there's a log file. So let me go ahead and download the log file, and then I can show you what the log file looks like. So once again, just click the download button itself, or you can right click on the link itself and say save link as. And it will just save this. Oh, okay, that doesn't work. So we have to click the download button this time. And then we save it as sample1.log. You can rename it to anything you want. So I will just save it as is. And then we'll take a look at it. Okay, so we have to go to the command line, and then we'll do an nvim. What was it again? Sample1. Yep, there we go. All right. So this is the history of how things got changed. Okay. In other words, every time I change the coefficient, it is registered. Every time I change E2, it is registered. But it doesn't do the work for you. It gives you a way to verify whether your program is working or not. Does that make sense? So does it help? Does it?
Yeah, that's right. I'm looking at it on here. Yeah, I see what you're saying.
Yeah. So if you once you implement your code, okay, the first test case you want to run through is this one, okay? And the way you run through your code is every time you change the coefficient, you put a breakpoint. Every time you change E2, you put a breakpoint. Every time you change E10, you also put a breakpoint. Well, if that continues, I'm going to go outside and tell those people to go somewhere else. Right. So when you look at this, it's like, oh, but we are only changing E2, I don't see any changes to E10. Well, it is all the way down, okay? So let me search for E10 equals to. So you can see E10 is changed all the way down here on line 116, E10 got changed. So that means when you are running your code, you need to put a breakpoint when you are changing E10. So let me give you a quick quiz here. In your code, when you make a change to E10, do you think you're incrementing or do you think you're decrementing E10 in this specific program? You're given with a negative E10 to begin with, and the objective of the code is to get it to 0. So do you think you'll be incrementing or decrementing? Incrementing, very good. Okay, so you should have only one line of code of your entire thing to increment E10. Put a breakpoint there. Okay. So once you put a breakpoint there, it would go from -47 to -46. At the same time, you want to check your coefficient. If your coefficient is not this particular value, something is not right. If your E2 is not this value, something is not right. Stop and debug the program. Is that okay? So this log file is intended to help you test your code and be able to detect when did my program go wrong, how did it go wrong. Yes, there was a yep.
I was going to ask, can you use helper function outside of like this? Like, can we declare new functions and then use them within that function?
As long as you do not call anything that directly do the conversion of the string and bypass them using your own logic to do the conversion, yes, it is okay.
Okay.
Yep. So you can definitely implement your own subroutine. The actual code, if it's done right, it's not really all that long. So it doesn't help that much by writing your own function. But if you feel like but I do want to write a function to do blah blah blah, because I want to reuse it or what I want to make it the code more modular, that's fine. It's not a problem. Yep.
How do you use the debugger to create a log?
How do you use a debugger to
Create like a log, because we don't have.
There's no easy way per se, okay, but there is a function, there's a command in the debugger that can track changes to a particular thing. I think it's called watching, so it's a watch expression. So you can use a watch expression if you want to, but generally speaking, if you use the watch expression, it'll just give you a lot of gibberish. So it's best to use the breakpoint approach and see whether you got to this point and everything is right, because if it's not right, then it's better to just look at the code and logically try to figure out why it is not doing what it's supposed to. Yes, go ahead.
Oh yes, is this log file, like, should we hit every single one of these steps? Like, did you go farther, or when we?
This goes all the way to the end.
So the end part is the result we should have.
Yes.
Okay.
So it goes all the way to the end, which means by the time you get to the end of the function, after your code runs, we should be expecting E2 to be negative 213. The exact value should be in the coefficient, and we should also be expecting E10 to be 0. So this one does spell out exactly how the structure should look like by the time your code is done. Is it a little bit long? Yeah, I mean, the log has 500 and something lines, but you're not going to have, you should not be looking only at the end result. You should be looking at the steps as it's making changes to E2 and the coefficient and E10. You should be checking and double checking, and try to match the behavior of your program with this log, of every step along the way. There was a hand. Nope. Okay. Any other questions?
So there's two different, okay, tell me if I'm wrong in this thinking. The way to get the exponent when it's less than 0 and when it's more than 0 is slightly different.
That is correct. This one only has to deal with when the exponent of 10 is less than 0.
So,
Yep. The other one will be an assignment next Tuesday. So if for those of you who look at this and go like, oh, I can get this done in the next 15 minutes, you can move ahead and actually deal with the other one too, because we know the next one is going to be having a positive exponent of 10 and trying to get it down to 0. So for those of you who get this done early and quickly, you can definitely just kind of implement the next one too, because that's your next assignment. Any other questions?
I don't know if this is, I don't know if this is thinking a bit too far into the future, but for the positive exponents, would that use the same program that we were given? It's like after we code the negative exponent, we would use the same program for the positive one, or
It's up to you.
Different assign?
Yeah, it's up to you, because the way I test each one is independent. So for the negative exponent assignment, I will only test it with a negative exponent. With a positive exponent assignment, I will only test it with a positive exponent. So they should not interfere. If you want to reuse the same code, it should not interfere either, because the code responsible for the code that is supposed to work with a negative exponent would not activate at all when the exponent is positive. So that's entirely up to you. Yeah. All right. Any other questions? So use this log file. Okay, this log file is important when it comes to testing your code and seeing whether it is doing what it's supposed to do or not. Are we good so far? All right. So start early with this assignment.
because over the weekend, I may not check my email as frequently. So, you want to be able to kind of get this started. Getting started today is not a bad idea. Okay, you go to the lab, get started with this one, and see how far you can go. Because I can come to your workstation and at least help you diagnose the program that you're writing. Anything else that you want me to talk about for this particular assignment? So a few things are, yes, go ahead.
I remember you talking about the condition that C times 2 is less than equal to max.
Yep.
int,
Mhm.
And you were talking about how like you have to like change something to not make that like.
Yep.
Go overflow.
Yep.
Is that something you can talk about right now, or is that something to figure out?
Well, I can talk about it, but I won't show you the code because that would be a little too obvious. Okay, so I can talk about it by looking at this particular program. And the question is, how do I assert this thing here? Okay, 2c or 2 times the coefficient is guaranteed to be greater than or equal to 2 to the power of 64 minus 1. So if you are to use the equivalent to C expression, that is guaranteed to be false. Because you're basically asking, is this 64-bit unsigned value greater than or equal to the largest value that you can have? And the thing that's greater than or equal to is that is supposed to be greater than and not the equal to is not supposed to be there. Let me go ahead and change that first. So the idea is you want to make sure that both sides are. No, it's greater than. Yep. Let me change that first, and then I will go back to the discussion. Okay. Yep, that was my bad. I used the wrong comparison. So it would be this one. Now this entire assignment is only worth 4 points, which is not a whole lot, okay? Because you remember many of your earlier assignments are worth what, 7 points already. So in terms of point value, it is not a lot. But it doesn't mean it is not important, because by doing this assignment, you will get a much better understanding of how floating point numbers work. And that is going to be in exam 2. Yep.
Wasn't there other stuff that, like just like typos you had in the,
Typos?
yeah,
Oh yeah, the expression versus the expressing.
Okay, good. Fine, we'll fix that too. Okay, we'll find expressing. Yep, there we go. This is supposed to be expression. There we go. All right. All right, yep.
So is a good way in code to like effectively check whether it's above that threshold to keep multiplying until it is and then divide afterwards.
Well, okay, division is a part of the solution, but not as you said. Okay. Yep.
I saw that in the log file. You had started out by incrementing the coefficient, I think it was, and E2, but then also after the last E10 dropped down to 0, you again increment. The
I would
coefficient.
double it again, because at that point it does not meet this requirement. So
Okay.
right after I divide, okay, let's think about this, okay? So when you, okay, let's just say that C is already the largest value you can fit into a 64-bit unsigned number, okay? After you divide it by 10, does it still meet that requirement?
No, but
Exactly.
at the end of the E10, wouldn't you have everything that you need, or
Say the one more time.
Whenever E10 goes off to 0,
Uh-huh.
you have incremented it again.
Okay, so you're talking about line 512,
Yeah,
where E10 itself is incremented from -1 to 0.
Yeah.
But you can see the coefficient got doubled 4 more times before I get out of the loop.
Yeah.
And that has to do with this number here is not the largest
Coefficient that you can fit in 64 bits. This is a little bit smaller than that. I need to double it 4 times in order to get it to become the maximum that you can fit inside a 64-bit unsigned loop. So you're making, so it's great. You're making an association of the 4 additional steps with the condition
of I need the coefficient or I need twice the coefficient to be greater than 2 to the power of 64 minus 1.
because I want all 64 bits to be in use in the coefficient. Is that okay? So you have to kind of think about the logic of how to do that, right? So that's part of the exercise, is to think about how do we write C code to perform all of these steps.
So since we're doing it at the end there, normally, or from what I understood, we were increasing its size so that when we do the division,
Okay, we're increasing,
when we're doubling,
when we're doubling the coefficient.
yes, when we're doubling, we're doing that so that we lose less when we divide it by 10.
Yes.
So if we're no longer dividing by 10, is there an actual like benefit to doubling it, or is that just to fit this standard for this?
Well, if I don't do this, then I really do not know how many bits are really in use in the coefficient, which makes it kind of a little bit harder to normalize
So it's
the
for
values.
standardizing.
It's for standardizing. Okay, there are other ways to standardize. I just chose to do it this way. All right. Any other questions? So remember, this file is here to really help you debug your program. Setting up breakpoints, single stepping, those are all really useful techniques to debug the program. Are we okay so far?
What time are we in the recording? What time are we in the recording?
What time?
For your
You don't have the recording timer?
probably.
Oh, you mean the,
Drive an hour.
like the current time?
It is, we're 1 hour into the lecture right now. Yeah, I forgot about that one. It still have the clock. It's just, I forgot to make it show all the time. So I can do that now, always on top.
All right, any other questions?
I'm not super comfortable with C, but I assume it's mostly the same. Is there anything you think we would try to use in C++ that would come to a point where, oh,
C and CL doesn't work.
that's it? Like it has.
Everything else, I mean, okay, so there are tons of stuff that you cannot do in C, but you can do in C++, like all the environment stuff, all the methods, all the abstract classes and stuff like that. All of those have nothing to do with this homework assignment. So from the perspective of just being practical, the only thing you really cannot do here is C and C out, which I really do not recommend, but if you guys want to do C and C out, you just have to change online GDB to C++, then you can use all your C stuff, C++ stuff. Alternatively, you can also learn how to use printf.
It's also not a thing in C.
C has no quote-unquote string, but it has string functions. So strcmp, string compare, string copy, they all work in regular C. It just doesn't have a specific class for strings. Yeah, a string is nothing more than a null-terminated array of characters in C. And in C++, they dress it up a little bit. I look at C as angel food cake, and the C++ is angel food cake with icing. It's pretty much the same stuff with more calories. Any other questions? So as I said, get started early because it really is not a really complex program, especially if you go back to one, the reading material, two, the lecture on Tuesday. Because then you can look at those the code, the pseudocode that I went through, you go like, oh, okay, we just have to convert this into C and go like, oh, okay, done. I gave you most of the logic already on Tuesday. All right, so if there are no questions about this, we're going to move on to some new material, and this would be a good time to mark the time. It is 6:33 p.m. We are moving on to some new material. So I'll go ahead and start with that. But if you have any questions, you can go back and ask those questions here as well. It's just that if I don't see any additional questions, I don't want to waste time, and I want to start with the new material. So we are starting with the next big module. I know the way I use the module in Canvas is kind of not the not the best way to use it. There's a lot of stuff. So we are now moving on to the von Neumann architecture and memory model. So this is the part that has to do with computer organization. The stuff before has to do with how data or how information is stored. How do we store values? Okay, we can deal with integers. Okay, unsigned integers, super duper easy, base conversion, right? Oh, but what if we want to store something that's negative? Oh, that's okay. We got the signed representation. But what if I want to store pi to 3.1415 blah blah blah? We got the double precision floating point numbers. Okay, so that's what the previous huge gigantic module is about. This module is about what is inside the processor. Okay, it's about computer organization. The class has changed its name from assembly language programming for microcomputers to computer organization and architecture. This is the part about the computer organization, what is inside the processor. So the first thing is I will do a quick introduction to John, J-O-H-N, von Neumann. Because I think it is important to understand a little bit of the context. So this is John von Neumann, definitely not, okay, well, I'll just put it this way. He's definitely no Steve Jobs, okay? But he makes a huge difference in terms of computer science. Alan Turing made a lot of contribution, and this is the other person who also made a lot of contribution. So you guys remember, we talked about how computers used to use electromechanical devices, relays, and motors and stuff like that. And back in those days, when you wanted to specify what the computer is supposed to do, everything is hardwired. Okay. In other words, you can point to a physical wire inside the computer and say, yes, that wire is responsible for this, or at least in part responsible for this particular behavior of the computer. We are taking the data from here to over here, and then we're adding these two values and store the sum over here. Everything has a wire, okay, a bunch of wires associated with it. So the question is, what if you want to change the program? What if you want to change the behavior of the program? You open up the computer, all you can see is a bazillion wires. You have to change the wiring to change the behavior of the computer. Is that okay? That's how computers used to be. So this guy came along and, okay, so the other thing is computer memory already existed. Because in order to do the computation, for instance, figuring out the trajectory of a shell from a battleship, okay, you have to have variables, right? Because you're not always going to point in the same direction, and the range is always going to be the same. So you still need memory to store things that are variables. So memory already exists. This guy came up with the idea of, well, what if we use the memory not only to store the data, but also to store the instruction? In other words, we'll use a part of the memory to store whatever data we're supposed to process, but we'll use also the same memory to also store instructions so that the memory, the instructions stored in memory will also be used to tell the computer what to do in what sequence and so on and so forth. That was his contribution, which to us does not sound like a big deal at all, right? Because that's what we're used to. But if without him contributing that particular idea, every time you want to change or patch a program, you have to open up the computer, look at those bazillion wires, and then look through the instructions, and then rewire, physically rewire your computer in order to change or patch your program. You guys are looking at me go like, so what? Well, next time you do any update to your apps on your phone or think of stuff like that, think about what if you cannot do that? What if every single change is physical? Okay, so that's his contribution. I'm not gonna spend too much time, and his history is also a very interesting read. So if you have spare time, it's an interesting story to read about his lifetime. All right, so getting back to all the relevant stuff, and we are moving on to this particular module, D flip-flop and other basic memory devices. So this is our new module. And all right, so the first thing we do is we will design an SR latch. And the way I describe an SR latch is not a diagram anymore. And then you guys go like, so what happened to Logic-Sim? Why are we not using Logic-Sim? Because I want to introduce a different way to specify a circuit without using graphical representation. And why do you think this is important? Why do you think it's important to be able to specify circuitry using just text?
This is gonna be on the test.
Sorry?
This is gonna be on the test.
Well, it is. It's going to be in a test. So in the next exam, I will give you the description of the circuit using only text. Okay, but that's just a byproduct. Okay, that's just a byproduct. Okay, let me ask: is anyone here planning to transfer to Berkeley? Okay. Well, I mean, it's you at least you have a plan. Okay, that's something that you're considering. So at Berkeley, they have a computer architecture class, basically a souped up version of an upper division of this class. It makes this class looks like child's play, or less than that. Okay. So the question is, and your assignment is going to be, okay, implement these really cool and fancy features on a processor. It's a 64-bit processor with all kinds of cool stuff already. So the question is, do you think you're going to design a real processor using a tool like Logic-Sim, where everything is graphical? And why not? Yep. And the pictorial representation is very difficult to edit, because every time you want to add a circuit, you kind of have to push everything else away a little bit, make room, stash whatever additional circuit you want to put into the circuit, and so on. And also try to imagine a 16-bit carry look-ahead adder. We did a 3-bit one, right? Let's imagine a 16-bit. And try to do it by hand. Now, the structure is not difficult, right? We know a way to generate the equation or the formula. We know the pattern. But to do it by hand is like, probably not. I mean, you can better spend your time on something else, okay? So the idea behind using text to represent the circuit is so that you can use a program to generate circuits. Once you understand the carry look-ahead structure, you write a piece of code, a subroutine, and you just say, oh, I need to figure out what is K16. Call the subroutine returns with a text description of all the bazillion AND gates and the few OR gates and you're done. Does that make sense? So having a text representation of a circuit allows you to specify complicated circuits using subroutines, loops, conditional statements, everything that you already know in programming. And that is why I want to give you some exposure to how to specify a circuit using only symbols and text. Is that okay? All right. So now we're going to convert this into Logisim, and I'm just keeping track of time. And I think I'm not going to take roll today, just because I think the time is better spent in doing this, even though I do have the roll stuff all set up already for today, but I'm not going to do it. Okay, so let's get out of this one and start up Logisim. All right, so let me see, where did I stash my Logisim stuff? Okay, go. All right, so Logisim started on the other side. Maximize it. There we go. All right, so I have to now alternate between the two screens. So this means we have two NAND gates, N1 and N2 are NAND gates. We have two input pins S and R. We have two output pins Q and NQ. So those are pretty easy to do. We just have to go to gates to get our NAND gates. So here we have the NAND gate here. And we need two of these, but I'm going to change the size and also the number of inputs before I duplicate. Control D is duplicate. So now we have these. We have two input pins, like so. We got two output pins. I'll put one here, and then we'll put another one down here. All right. So it's good, it's useful to name the pins. So we'll use NQ to label this one, and Q to label this one. This is going to be the gate that we call N1 in the text. This is going to be N2. This is going to be S, input pin S, and this is going to be input pin R. All right, so we got the components. So when you go back to the code here, using traditional C++ notation, this is the name of the class, which is the same thing as the symbol on the left-hand side of Logisim. And these two are instances. So we're basically instantiating two NAND gates, N1 and N2. We have two input pins, S and R. We have two output pins, Q and NQ. Okay, so that's what that portion of the code is doing. So the next portion specifies the nodes. So each node is basically a piece of continuous copper that connects the ports of components. Okay, so every time you draw a wire from one component to another component in Logisim, you are extending a node. But a node doesn't have to be just going from one particular port to another port, because everything that connects to that particular wire, they're all called the same node. So in this case, we want a connection between the pin from input S to the first input pin of N1. Okay. And we're going to do it like this. Okay. Connect this one to the first input of N1. And then the other one is from R to the second input pin of N2. So it's kind of a mirror. In fact, this entire circuit is symmetrical vertical wise. Okay, so you can kind of imagine if you put a mirror in the middle, the two sides would look identical. And then we have something that's a little bit more complex. So this time we have a node that has 3 ports. So we are connecting all 3 together. The output of N1 connects to the first input of N2, but it also goes to the Q of the pin. So we'll go ahead and implement that particular node. So what that means is we have one wire going this way, but it is the same node, and this one also connects this way.
So it is considered exactly the same node because if you change to the poking tool and you click on this thing, the entire thing is highlighted. All right, so now we're working on the last node, which is symmetrical. It goes to the output pin like this, but at the same time, quote unquote, it also feeds back to the second input of N1. There we go.
So this little circuit here only makes use of 2 NAND gates, which means we only need a total of 8 transistors. 4 p-type transistors, 4 n-type transistors, and we can implement something like this. So the question is, what does it do? How do we analyze something like this when it has quote unquote feedback kind of thing? Okay, so we want to figure out, okay, how do we deal with this? And I'm looking at the time, we're out of time. So we'll go ahead and think about how to track changes or how we track the propagation of changes with a circuit like this. Now,
it would be very helpful to read over the weekend because I know some of you are just leaving right now and you're going home. So it would be very important to read section 3 of the notes here. And there's one more. If you go all the way back to Canvas, there's also, where is it? There's also this little link here. It's a very, very short module, but it talks about how to track change propagation. So read ahead of time because those are, I would say they're not really complex concepts, but it does take some time to get used to. So read those 2 things that I just mentioned and also work on the program over the weekend. And I will see some of you over in the lab. Yep. Right, this one is no good because it's a longer time frame thing. So I just open it to
The assignment, I know we're for this assignment, I know we're trying to avoid the overflow. Or like C, could we just like, this like measure if it's greater than this one?
Yep. That's it.
I had a quick question regarding GDB and C. So when I took 360 and 400,